Hello, everybody. Today, we're going to be talking about Earth's atmosphere. So this unit, of course, is called Meteorology and Oceanography, affectionately called METOC. So we're actually start with the meteorology part, and then we'll get into the ocean part. So um, today, we're just going to look at how our atmosphere has changed over time, some of the big events that changed our atmosphere and produced it or caused it to be like it is today. We'll look at some characteristics of the atmosphere as far as like levels and how temperature and pressure change with elevation. And then we'll get into some very basic meteorological concepts, some basic concepts in weather that you'll need to have moving forward. All right, so let's just get right into it. So the early Earth atmosphere. When we get to astronomy, we'll talk more about how the theories for the formation of planets and for the formation of the Earth. But basically, the early Earth atmosphere, we believe, was just a collection of hydrogen and helium. Hydrogen and helium, of course, are the two most plentiful elements in the universe. It's also the two the elements that go into making a star. Some of that material was held onto by gravity around the Earth. And so that probably made up our first atmosphere, hydrogen and helium. These are very light molecules, gas molecules. So these molecules rose to the surface from outgassing, which is basically volcanic eruptions, or as asteroids or comets impacted the Earth, the gases that came off. This early Earth atmosphere did not last long. Because hydrogen and helium are such light molecules, they were pretty easily swept away. So the next big change, as hydrogen and helium escaped out into space, volcanic eruptions, which were very frequent in the early Earth, think back to the Hadean eon, Hades, outgassing from volcanoes probably produced our next big atmosphere, primarily carbon dioxide, sulfur molecules like sulfur dioxide, ammonia, some water vapor, some elements like argon and neon. But the big ones there, carbon dioxide, and even some methane as well. So these volcanic eruptions probably produced our next big atmosphere. Some of these compounds are, of course, broken down into other simpler compounds. But then we have a big game changer. Simple organisms began to develop after the oceans formed. These simple organisms, some of them could photosynthesize, and the most important one was probably cyanobacteria, so blue-green algae. It's a photosynthesizing organism producing oxygen through photosynthesis. So it pulls in carbon dioxide first in the oceans, and once the oceans were oxygenated, the oxygen would then escape into the atmosphere, forming our next big atmospheric change. So at about 2 billion years ago, there was enough oxygen in the atmosphere that it's about the level of what it is today, just about. So those early organisms created our next atmosphere, which allowed life to develop on land. So how did those oceans form? Most scientists hypothesize that water probably came from comets. Comets are icy objects from the outer solar system that contain a lot of water ice, a lot of frozen dry ice or frozen carbon dioxide, some metal, some dust content, even some organic molecules, which form I don't want to say spontaneously, but organic molecules just mean is carbon-based. So organic molecules like methane, ammonia as well, which isn't organic, but very easily forming molecule. So all of those probably were delivered to the Earth by comets. Quick question, were our first oceans salty? Probably not. First oceans were probably fresh, and then as minerals were broken down through chemical weathering processes, became salty later. So our atmosphere today is primarily nitrogen, 78% nitrogen, and about 21% oxygen, with that remaining 1% primarily argon, and then that other is carbon dioxide, methane, water vapor. Now, of course, carbon dioxide can have a huge impact on other things because it can hold and trap heat, but our atmosphere is primarily nitrogen and oxygen. So how do these gases move throughout the atmosphere? Well, they move in cycles. So the first one is the nitrogen cycle. The nitrogen cycle is a process where nitrogen moves from the atmosphere into living things and then back into the atmosphere. Some of the main parts of the nitrogen cycle: nitrogen fixing bacteria in soil take that nitrogen gas and form nitrogen compounds, which can then be absorbed by living things. So those nitrogen compounds are either pulled in by plants, or animals will eat those plants to get that usable nitrogen. Some of that nitrogen comes back into the soil through the waste products of animals. Some of that nitrogen goes back into the atmosphere from decay. So once the organism dies, bacteria, fungi start to break down that organism, releasing that nitrogen back into the air. Of course, oxygen, 21% of our atmosphere, it is constantly cycled primarily through cellular respiration and photosynthesis. So in photosynthesis, we have carbon dioxide, we have water and sunlight being used to create a sugar molecule like glucose. Then respiration, either the plant or an animal that eats that plant will break that glucose molecule apart, producing water vapor and carbon dioxide. And that brings us to the carbon cycle. Carbon, of course, is essential for all living things. Carbon dioxide, lots of different sources for carbon dioxide in the air. We have cellular respiration coming from plants or from animals. We have combustion, producing carbon dioxide, both human and natural fires. We have decomposition, and again, cellular respiration of living things. Decomposition, of course, when they die, they release carbon back into the atmosphere. So some of that atmospheric carbon dioxide is dissolved in water, and then it's used by marine or freshwater photosynthesizers to produce oxygen. But then you also have erosion, taking some of that carbon dioxide, pushing it off into water systems as well. That's basically it. And so this constantly moving carbon around. Water. Water is essential for all life. The water cycle, of course, affects how animals and plants survive, but it also has a big impact on weather and climate, as you will see. Ozone. There's a layer in our atmosphere that contains this molecule called ozone, which is O3, it's 3 oxygen atoms. Ozone is extremely important. As we were talking about earlier, the early Earth atmosphere, these living things were pulling in carbon dioxide and producing oxygen. Once the oceans were oxygenated, that oxygen was released into the atmosphere. Oxygen can be broken apart by radiation from the sun. When radiation from the sun hits an oxygen molecule, it can split, which will then recombine into O3 or ozone. Here's the thing about ozone. It absorbs lots of solar radiation. Ozone is the planet's sunscreen, for lack of a better word. It's always amazing to me that living things made an environment for other living things. So these early cyanobacteria and algae that produced oxygen to go into our atmosphere, it created the ozone layer, which absorbs solar radiation. Without that ozone layer, life on the surface could not have existed or evolved. So life created a barrier, a protective layer for other life, which is really neat. But ozone is extremely important because it absorbs ultraviolet radiation, without which living things would not be able to tolerate for very long on the surface. So let's take a look at the layers of the Earth's atmosphere and some of the characteristics, basic characteristics for each layer. So as we get into meteorology, you'll see that almost all the weather and things that we talk about occur in this one part of our atmosphere, the bottom part, the troposphere. But these other layers have really interesting characteristics as well. So in this diagram, you'll see that it's organized by layer, and we're going to start at the bottom, the troposphere. Now, the troposphere is the bottom part of Earth's atmosphere. It extends to about 12 kilometers, 6 to 7 miles or so. It changes. It undulates. It's a fluid, so it can move up or down depending on conditions. The troposphere is the thickest part of the atmosphere. I think by mass, it's like 90, 95%. It's a very high percentage, 75 to 95% of all of our atmosphere is contained in this layer because it's the densest layer. All life and nearly all weather occur in this layer. As you move up away from the troposphere, or away from the surface in the troposphere, two things happen. One, the air becomes less dense. There's less air molecules around. This is why people who go up to Mount Everest will need oxygen because there's just so little amount of air there. The second thing that happens is that as you move up through the troposphere, it gets colder. This makes sense because when you go up on top of a mountain, it could be 10, 15 degrees colder than it can be in a valley. There's a really good reason for this, and it's kind of counterintuitive for a lot of students. When the sun shines, it heats up the ground. That ground will in turn heat the air that it's touching through conduction, basically, the heat transfer of touching. So as you get away from that heat source, the surface, it gets colder and colder and colder. Kind of an interesting idea. So sunlight shines down, hits the surface, and heats the air directly above it. Such that if you move away from the surface, it gets colder and colder and colder. So as you move up in this layer, not only does pressure decrease, but temperature decreases as well. The stratosphere. So this one extends from the bottom of the troposphere, or it's going to be the top of the troposphere, to about 31 miles. This one, we have something different happening. The temperature starts to increase as you move up. Now, again, the air is becoming thinner and thinner and thinner. There's less air molecules. This air is also very dry. There's almost no water vapor in this layer. The other big thing about the stratosphere is that it contains our ozone layer. So inside of the stratosphere, there is that layer of ozone, O3, that absorbs solar radiation, making life possible on the planet. Then we get to the middle layer called the mesosphere. Meso means middle. Now the mesosphere is from about 30 to 50 miles or so. It's very thin here. But if you have a fast enough object hitting our atmosphere, the air is just thick enough here to where the object will start to glow or ablate. So let's say it's a meteoroid, just a piece of rock. It's coming flying at the Earth at about 25,000 miles per hour, extremely fast. When it hits this layer, there's enough air molecules here to cause friction on that rock that causes it to heat up and to glow. It's called ablation. And those are what shooting stars are. The mesosphere is also very cold. Now, the air molecules can be heated up and they can move around, but because they're so far apart, it's really difficult for it to transmit that kinetic energy. So the mesosphere is actually the coldest layer. Then we have the hottest layer, the thermosphere, heat. Temperatures here are very high. So solar radiation, there's not a lot to absorb that energy. So objects, when they go into the thermosphere, can heat up very, very high, more than 2,000 degrees Fahrenheit. Technically, this is where space begins. Now, different textbooks will say different things. They may say space starts here. They may say the exosphere, which we'll talk about in just a second. But for the most part, this is where we think of space beginning. It's also a very thick layer from about 50 miles to over 400 miles. Again, different textbooks will say different things. The International Space Station actually orbits in this layer, so there's almost no air molecules here. Then finally, we have the exosphere. There's no real exact dividing line between our atmosphere and space. It just gets thinner and thinner and thinner, and basically you get far enough away, there's almost no air molecules. The exosphere is very high. It's above 440 miles or so, and most satellites orbit in this layer. So that's it. Troposphere, stratosphere, mesosphere, middle, thermosphere, exosphere. So I have this nice little graphic to kind of show you a few things. Troposphere, down here at the bottom. All weather, all life occur here. And that's why you see this cloud and it just hits the top of the troposphere. There's a layer, a very distinct layer that stops water vapor from moving into the stratosphere. And so that's why these clouds will make these anvil shapes, because they hit the top and then spread. So that's the troposphere. Above there, we have our stratosphere with the ozone layer. Have some spy planes that can actually go in there. Most commercial jets are right at the top of the troposphere, at the bottom of the stratosphere. We have then the mesosphere, very thick, again, not to scale. Most meteors burn up here. And then the thermosphere here, and then beyond that, way up would be the exosphere. So also over here, you can see a temperature line. As you move away from the surface into the troposphere, the temperature drops. In the stratosphere, after you pass the ozone layer, it starts to rise. The mesosphere, it drops way down. That's the coldest layer, and then the thermosphere would go way up. So again, here's another view. How does temperature and air pressure change without altitude? Drops in the troposphere, rises in the stratosphere, drops in the mesosphere way down, and then comes back up in the thermosphere. So temperature kind of goes through this W, sideways W, or M, however you want to think of it. But then we also have pressure. If you take a look at this little black line, this represents pressure. As you go up from the surface, pressure decreases. And by the time you get into the top of the stratosphere, very few air molecules. And then they just get continually thinner and thinner and thinner as you move up. And then the last one is water vapor. Almost all of our water vapor is contained in the troposphere. So once you hit the stratosphere, water vapor drops off to absolutely nothing. Again, that's why when clouds, they rise up really high into the troposphere, they can form that anvil shape and spread out because the water vapor is not allowed to move past that line called the tropopause. It separates the troposphere from the stratosphere. All right, so that's the atmosphere. Let's talk about weather. Just some very basic concepts. So we'll start with this quote that we talked about earlier. Our planet is invested with two great oceans, one visible, the other invisible, one underfoot, one overhead. One entirely envelops it, the other covers about 2/3 of its surface. So this is Matthew Fontaine Maury. He's a Virginia native and is also the father of modern oceanography. The ultimate driving force for all weather is the sun. So the sun's energy, you think about the water cycle, it drives the water cycle. It causes heat, and that heat is, of course, going to spread out throughout the planet and try to mix as the air masses move around. The sun is our driving force for all weather. Speaking of heat, let's talk about heat transfer. This hopefully just a review, but when we talk about weather, all three of these have their own effect. There are three ways that heat can be transferred from one object or one material to the next. There's radiation, which is the transfer of heat through electromagnetic radiation. As material absorbs that electromagnetic radiation, it re-emits that energy in the form of infrared heat. So radiation, light shining down, it absorbs. Then there's conduction. Conduction is the heat by direct contact. So putting your hand on a hot plate or hot stove, that heat is transferred to your hand by conduction. When we talk about weather, what we're talking about here is the direct heating of the air directly above the surface. So radiation heats that surface up, and then the surface heats the air that it touches by conduction, direct contact. The last one is convection. When that air is hot, it becomes less dense and it rises. As it rises, a couple of things happen. One is it gets further away from that conductive surface, so it gets cooler. You also have a pressure drop, and that also has its role to play in how things cool. But for right now, radiation heats the surface heats the air above it through conduction, and then when it rises, gets cold, then sinks and gets reheated again, that's convection. Seasonal solar radiation. All right. So there's a question in your notes that says, what areas of the Earth receive the most direct solar radiation? Most of you will immediately say the equator, and you're right. I'm not saying that's wrong, but we're going to expand that just a little bit. There are two very special lines across the Earth, and they occur at 23.5 degrees north and 23.5 degrees south. If that number sounds familiar, it should, because that's our tilt. The tilt of the Earth's axis is at 23.5 degrees. That makes these two very special lines. 23.5 degrees north latitude is called the Tropic of Cancer. 23.5 degrees south latitude is the Tropic of Capricorn. Because Earth is tilted, different parts of the Earth receive different amounts of solar radiation. So we have these very special days. The solstices. The solstice in December is the winter solstice for us, and in June it's the summer solstice. Let's start with summer. So if you see in this diagram right here, around June 21st, June 22nd, the Earth, as it makes this transition around the sun, the Earth is pointed as much as it can towards the sun. Imagine my head's the sun. Earth is tilted toward it. So notice that the axis is pointed as much as it can. That means that at noon on that day, at 23.5 degrees north latitude, the Tropic of Cancer, the sun would be directly overhead, like directly. You would cast the smallest shadow. After that day, the sun gets further and further and further down, going from June to fall. So in the fall, and the spring, we have what are called equinoxes. The equinox, the sun would be directly overhead at the equator. So if you were at the equator around around September 21st, 22nd, 23rd maybe, the sun would be directly over your head. You would cast the smallest shadow. The sun would continue to drop a little bit more each day. And then we get to the next solstice, the December or winter solstice. At the December or winter solstice, at 23.5 degrees south latitude, the Tropic of Capricorn, if you were there, the sun would be directly over your head. You would cast the smallest shadow. And then we continue back on around to the spring equinox. And at the spring equinox, again, if you're at the equator, the sun would be directly over your head. So what parts of the Earth receive the most direct solar radiation? Is a constant cycle between 23.5 degrees north to the equator to 23.5 degrees south. It just goes back and forth throughout its transit every year. So where we are at about 37 degrees latitude, the sun never reaches overhead. We're too far up on the Earth. But during our June solstice, the sun would reach its highest point in the sky. And in December, it would reach the lowest point in the sky. So I have a quick little interactive here. Please explore that, especially if you had trouble in the past learning and understanding seasons, but please take a look. And I'm just going to read you what I wrote for an explanation here. Direct sunlight cycles between the Tropic of Cancer and the Tropic of Capricorn. During our summer solstice and winter solstice in the southern hemisphere, got to remember they're always opposite. Around June 21st, the sun hits directly overhead. Around September 21st, our equinox, directly over the equator. During our winter solstice, the southern hemisphere's summer solstice, it would be directly over the Tropic of Capricorn, and then it goes right back to the equinox. Hopefully you can see this picture. This picture is a very special type of picture called an analemma. In an analemma, a camera has been set up permanently for a length of time. In this case, it's a year. Now, this picture was taken right outside of Sicily, Italy. The camera takes a picture every few days ago, every week or maybe 2 weeks or so, and it's pointed directly at the sun. And so it takes a picture on that day and then waits another week and then takes it at exactly the same time in exactly the same place. All those pictures are kind of put together into one. And what you see is this weird figure 8. This is actually the sun's transit throughout 1 year. So at this topmost point, this is the summer solstice. So that is when the northern hemisphere is getting its most direct heating. The summer solstice around June 21st, the sun would be directly overhead at the Tropic of Cancer at 23.5 degrees north latitude. It's our summer. It's the longest day of the year. We have our most daylight. So you can see it's way up high in the sky. Right here is the midway point. This is the equinox. This is equal night, 12 hours of daylight, 12 hours of night, happen in September and for our fall equinox, and then in March for our spring equinox. That's that midway line. Down here at the very bottom, we have our winter solstice, where the sun reaches its lowest point in the sky. We have our shortest day of the year. So when we talk about how the sun heats the earth, the part of the earth that is heated most directly is around the equator from 23.5 degrees north to 23.5 degrees south, and it constantly moves back and forth. Those parts of the earth are going to receive their most direct heating. As you move away from those points, you have less direct heating. So what is the point of weather? What does it do? Well, if you look at this chart here, we have equator at 0 degrees. You can see how this area from between 23.5 north and south, you can see how it's getting a lot of heat, but that heat has to go somewhere. Our atmosphere conducts and moves that heat around to other cooler places. And so you see the heat spreading out both north and south of the equator. Weather distributes heat energy from equatorial regions to the rest of the planet. This graphic shows you a little bit about our solar radiation budget. If we think of all the sunlight hitting the Earth as 100%, some of it's scattered back into space by the atmosphere. Some of that heat is redistributed out in space just by cooling. Some of it's reflected from clouds. So if we play with this, formula, how much energy we receive versus how much we put back out, we can either heat the planet or cool the planet. And right now we are in a situation where a lot of that heat is retained in our atmosphere due to carbon compounds and methane as well. And that has played with our climate, slowly increasing it. I made this graphic a long time ago, just a very simple way to help explain the global radiation budget, but also so that you can see different forms of heat transfer in the system. So some of the heat, of course, is radiated down, heats the surface of the planet, causing conduction right here at the surface, then convection, and then, of course, radiation. All right. So we've talked a little bit about heat. Let's talk about wind. Wind is just the movement of air. So how does wind move, or in which directions does it move? So wind air always moves from or I should say, heat energy always moves from a hot object to a cold object. So the areas of the planet that are heated up the most around the equator, some of that heat energy is going to move from hotter areas to cooler areas, both north and south of the equator. So this causes, you can see down here in this little graphic, how the heat is being distributed both north and south. If the Earth did not rotate, that movement would be straight. But we know our Earth rotates. So what does that effect have on our wind? Because the Earth rotates on its axis, air that's moving from the equator, both north and south, is deflected. If you're in the northern hemisphere, from the perspective, if you were looking down, moving north, it actually curves over to the right because the Earth is rotating counterclockwise. If you're in the southern hemisphere, it actually moves towards the left. It's called the Coriolis effect. This is the explanation for hurricanes and their motion, for why things seem to rotate and move when we talk about wind. So I have a video, so simply put, on the Coriolis effect. We're going to talk a lot more about the Coriolis effect, but for right now, what I want you to understand is that because the Earth rotates, it causes wind to move and change direction. It doesn't just move from the hot equator to the cooler latitudes. Because of the rotation of the Earth, it causes the air to move off to the right in the northern hemisphere, and it moves off to the left in the southern hemisphere. The Coriolis effect is the circulation of the atmosphere and of the oceans because of the rotation of the Earth on its axis. And you'll see here in this little diagram, the arrow is moving off in that direction. Think of it from the perspective of the arrow. It's actually moving to the right. And here, coming from the equator, again, moving off to the right. You go below the equator, it reverses, moves to the left. So real quick demonstration of the Coriolis effect. And please watch this video, but just real quickly, you have a platform. These two guys are just going to throw a ball back and forth, no problem. But what happens when we start to rotate the platform? See how the rotation of the platform is counterclockwise? And so when they throw the ball actually looks like it moves off to the right. That is the Coriolis effect, simply put. All right. Like I said, we're really going to get a lot more into the Coriolis effect and when we talk about global wind belts, but I just wanted to introduce that concept to you right now. Again, in the northern hemisphere, because of our counterclockwise rotation, objects deflect to the right. In the southern hemisphere, objects deflect off to the left. All right, so that's all I've got for now. We're going to get into a lot more specific details on wind motion, global circulation belts, and going to move into air masses and some real specific details in meteorology. But hope you learned something. If you have any questions, as always, please let me know.